Since the time you have begun algebra, you have always graphed all of your equations, all of your functions, all of your plotting points has been drawn on what we refer to as the rectangular coordinate system, sometimes referred to as the Cartesian coordinate system, named after Rene Descartes, who was the first mathematician. He was also a philosopher and so on, but he had his hand in mathematics and gave us the first opportunity to start graphing on this rectangular coordinate system. Now, the way that the rectangular coordinate system looks or works is that we would always start with the origin being kind of the base point. And if I wanted to look for where these points were, I have 4 points plotted in the X and Y coordinate system here. In order to plot that point, I'd have to go 4 units on the x-axis, 2 units on the y-axis, and notice that I'm drawing those lines parallel to each of the axes, which is why this point here is the point 4, 2. And likewise for any other points, I'd have to, in this case, go left 3, which would mean that my x-coordinate would be -3, and I have to climb 5 units, which is why my point back here would be the point -3, 5. And likewise, something over here in the first or the third quadrant, I'd have to go back 1 and down 4, which is why this point is -1, -4. And this is what we've been used to from the time that we began graphing and plotting points. And this is a good rectangular, or this is a good coordinate system for graphing a lot of different types of functions. We graphed sine curves here, right? We graphed parabolas on this coordinate plane. We graphed circles on this coordinate plane. We graphed all kinds of different shapes on this coordinate plane. But now that we've learned about trigonometry, it turns out that there is a new type of coordinate system that can be really helpful for us to graph a lot of other types of graphs that would be very difficult, if not near impossible, to graph on the rectangular coordinate system. And this is what we refer to as the polar coordinate system. And the deal with the polar coordinate system is that this point right in the center is not called the origin, it's called the pole. So the pole can be thought of as like the North or South Pole on our Earth. And essentially we can see that each of these concentric circles are a certain distance away from that pole. For instance, here is a concentric circle, and here's the next one. And I also see one way out here. And each of these concentric circles have a certain radius that's a certain distance away from the pole. So if I wanted to find a point or draw a point like this one right up here, where it used to be the first quadrant, the way that I would look at this now is that I would look at this in terms of how far away it is from the pole, the directed distance, as well as the angle that I had to turn through in order to get to there. So basically, if we know that this is the angle of 0, then in order to turn to this particular point, I'd have to go through a particular angle, and I'd have to travel out a certain distance. We refer to that angle as r. I'm sorry, the angle is theta. We refer to the directed distance as r. And therefore, this point out here would be defined by r comma theta. So we always put our r value first and our theta value second. So this shouldn't be too surprising because we've actually already done this type of work on our rectangular system, where we've labeled this quantity horizontally as x, this as y, and this distance as our r, where this is the angle through which we're turning. But now what we're doing is looking at this from a different perspective and actually looking at it as a point in the polar coordinate system. So the way that we would describe this point if you see that each, it looks like every other, I'm going to make every other hash mark on this axis, I'm going to make every other hash mark a radius of 1. Okay, so in other words, each radius is going to be 0.5 or 1/2. So every 2 radii, I'll just make them equal to 1. So that would be 6, 7, 8, and 9. All right, well, if I want to see where this is, we should recognize that I am on the 3rd concentric circle here, the concentric circle where r is equal to 3. And therefore, my point would have an r value of 3. The angle is obviously the angle from our unit circle. That angle is pi over 6. So although I know that every point in the Cartesian coordinate system is going to look like x comma y, never every point in the polar coordinate system is going to look like r comma theta. And so if I take a look at a different point, maybe the point up here in the 2nd quadrant, I should first of all recognize that it's at a different angle. That's obviously at an angle of 2 pi over 3. So I would rotate 2 pi over 3 units and then walk out however far that radius is. And therefore, that radius is going to be at 8 units away. 2 concentric circles before the end, which you can see over here. And therefore, my point would be the point 8, 2 pi over 3. But notice that I could actually write that in multiple forms as well. There's an infinite number of ways that I could write that point. I could also write this point by saying 8 and negative 4 pi over 3. Which would mean for that point, I started at the positive x-axis and went down and around. Or I could have come up with another coterminal angle. Perhaps I came up with the angle of 8 and I added 2 pi or 6 pi over 3 to get the point 8 pi over 3. So that's another potential point. Turns out that you could actually come up with this in a slightly different way as well. What you could also think of is pointing in the opposite direction. So notice that this direction down here would be at the angle of 5 pi over 3. So another way that I could actually describe a point in polar form is by pointing in the opposite direction, which would be at 5 pi over 3, and then walk backwards 8 units. So the way that we walk backwards is by making my r value negative. So this is the first time in trigonometry where we've determined that an r value could in fact be negative. It just means go in the opposite direction of the angle we're pointing in. And so there are an infinite number of points that we could plot, or an infinite number of ordered pairs that we could use in order to describe a point in polar form, even though there is only a single point in rectangular form or a single ordered pair that describes any particular point. So let's just take a look at a couple of these other points that are on the x-axis here. It looks like I've gone back 1, 2, 3 concentric circles. And so this has a radius of 3, and it has an angle of pi. So 3 comma pi would be the point in polar form. I could have also written it, if I chose to write it with a negative radius, I could have written it as negative 3 by pointing in the exact opposite direction of pi, which would be at the point 0, negative 3, 0. Or I could write it as negative 3, 2 pi as well. Okay. And so notice that we have a few relationships between the polar form and the rectangular form, and we've already dealt with these quite a bit when we were dealing with vectors and with complex numbers. But we should also recognize that x is equal to r cosine theta, which is a way for us to change from r's and thetas into x, and y equals r sine theta. We also have a way to find r, and we have a way to find theta. We could also recognize that tangent theta is equal to y over x, or the opposite over the adjacent. We could also see that by the Pythagorean theorem that r squared is always equal to x squared plus y squared. So this is actually a very helpful little table in order to show us all of the different equations that we're going to use to convert from polar form back and forth into rectangular form. So to come up with a few of these points by plotting them by hand here, let's say we wanted to plot the point 2, 30 degrees. So even though we read this with r first and theta second, it's important that we first of all change or rotate first and then walk out. So we're obviously starting at the pole. And let's just assume that on this diagram, r is equal to 1. So each of our concentric circles is a radius of 1. So this would be 1, 2, 3, 4, 5, and so on. Okay. Sometimes it might be scaled different, so we just have to pay attention to that. But notice that 30 degrees is actually the same as pi over 6. So we change this to the point 2 pi over 6, and now we're going to be pointing in the direction of pi over 6. Only we're simply walking out from the pole 2 concentric circles along pi over 6. So when I look at 2 pi over 6, that point will be here. So what about -4 2 pi over 3? Okay, so here's 2 and 30 degrees. All right, let's take a look at -4 and 2 pi over 3. So first of all, it says turn towards the angle of 2 pi over 3, which is this angle right here. And now it says walk backwards 4 units, which really means that we are pointing in the exact opposite direction, which means we are walking backwards 4 concentric circles, which puts me to this point here. And therefore, that's the answer of -4 and 2 pi over 3. Which you might notice we could also write as moving +4 in the positive direction of 5 pi over 3. So those are both actually equivalent to each other. Let's go ahead and take a look at 5 and -pi over 4. Well, now notice that -pi over 4 means that I'm going to start at 0 and go down and around clockwise. So I'm going to go at pi over 4, -pi over 4 is this angle here. And now what we're doing is walking out 5 concentric circles. So we're walking out to this point in the XY plane. But it's really not the XY plane, because now we realize that the concentric circles are telling us how far out to walk, and therefore we've got our answer of 5 -pi over 4. We could also write this, if we would like to, as 5 and 7 pi over 4, which would simply show us the exact same point, because I'm starting at the positive x-axis and rotating around counterclockwise. So each of those individual points are nothing more than just a distance away at a given angle on our concentric circles. We'll take each of these values now and convert them into rectangular form. So let's look at 2 and 30 degrees. First of all, recognize that 2 is my r value and 30 degrees is my theta value. So based on that, we should be able to find out what that point is if we were to write it in the x and y plane, which means how far would I have to move right and how far would I have to move up. Okay, well, I know that x is equal to r cosine theta, so 2 cosine of 30 degrees. And I know that y is 2 sine of theta, or 2 sine of 30 degrees. And now based on our unit circle, we find out that x is equal to 2 times root 3 over 2, which gives me a value of root 3. And over here, sine of 30 degrees is 1/2, so we've got 2 times 1/2, which is y equals 1. And therefore, this point over here could be rewritten in rectangular form as the point root 3, 1. Which makes sense because that would be in the first quadrant, which is a positive x value and a positive y value. Let's take a look at that next one. Let's say we have -4 and 2 pi over 3. So that's the same idea. We know the r value and we know the theta value. So now we should be able to find out our x and our y just by using our formulas. So x is equal to -4 cosine of 2 pi over 3. And we know that y is equal to -4 sine of 2 pi over 3. Okay, well, cosine of 2 pi over 3, remember that's a second quadrant angle and it's steep. So we know that that's -4 times -1/2. While my sine value at 2 pi over 3 is going to be the y value at 2 pi over 3, or positive root 3 over 2. Which would mean that based on this, we would get an x coordinate of 2, and we would get a y coordinate of -2 root 3. But again, that should make sense because of the fact that if this point is in quadrant 1, this point down here should be in quadrant 4 with a positive x and a negative y. But that makes sense because now notice where that point is, it's down in quadrant 4. So we can always convert. We could say that 230 degrees is equivalent to root 3 and 1 in rectangular form. Or we could say that -4 and 2 pi over 3 is equivalent to 2 root 3 in rectangular form. Now we're very familiar with equations in rectangular form, which means that they would be equations that have a y and an x. So maybe y equals 2x minus 3. That's a linear equation, it's rectangular. Or if I were to draw or write a circle, x squared plus y squared equals 4. There's a circle. Or maybe I write y equals x squared minus 5. There's a parabola. So these are all rectangular because the variables are y's and x. But some examples of some polar equations might be r equals 3 sine of theta, or r equals 2 plus cosine theta. Or maybe it doesn't even need to have a trigonometric function and it's just r equals theta, or r equals 4. These are all equations that are in polar form, which means in the rectangular form, typically you have an input of x and your output is y. So you plug some quantity in on the x-axis and you get the corresponding y coordinate. But now when you take a look in polar form, the input is going to be an angle. The output is how far you walk in that direction. So instead of having to walk left or right and then up or down to get to a certain point, we don't do that anymore. We now just say from the horizontal, rotate through a certain angle and then walk a certain amount in that direction. That's why it's referred to as r and theta. So let's go ahead and take a look at how to convert from one form to another. Now in this example, we should recognize that y equals 2x minus 3 is a linear function. And remember what a function represents. We're basically showing that all of these are in terms of x's and y's. And other than this circle right here, we can often replace them or write them as y equals some function of x. So we oftentimes are just trying to solve for y when we're converting into rectangular form. But you might notice what's common over here is that all of these have solved for r. More specifically, r as a function of theta, which means that if we're going to convert this equation into polar form, by the time we're done, we should have r is equal to some function of theta. So let's start off by recognizing what we're given. We're told that y is here and x is here, and we know that x is r cosine theta and y is r sine theta. So we could rewrite this as r sine theta is equal to 2 times r cosine theta minus 3. And so although this is already in polar form, it's not the best form because we haven't solved for r. So anytime you see r on both sides of the equation, you just have to simply move those terms around. So we have r sine theta minus 2r cosine theta is now equal to -3. And now you can recognize that pulling out r gives me the value sine theta minus 2 cosine theta equals -3. And so our last step is to divide by that quantity in parentheses, which means that r is equal to -3 over sine theta minus 2 cosine theta. And so what we should realize about this is that if you were asked to graph that equation, it would sure enough turn out to be linear, just like the original equation. They're going to have the same graph. It's just that the form of their equation looks different because this polar form is now going to be r in terms of theta. Let's go ahead and take a look at converting one into rectangular form. Well, if we have this equation in polar form, we want to now change this into x's and y's. Now, unfortunately, not all rectangular equations will be able to be rewritten as y as a function of x. It's possible that, like a circle, we might have both variables on one side. It just depends on what form we're looking at by the time we're finished. So let's take a look at this equation right here. And what we need to do is somehow replace all of our r's and our thetas or sine thetas with x's and y's. And so first of all, we should recognize from sine theta that y is equal to r sine theta, which implies that sine theta could be rewritten as y over r. So that might be a good starting point. Let's start by writing this as r equals 3 times y over r. Now we could rewrite r as the square root of x squared plus y squared. But if we did a little algebra here, if I multiply both sides by r, then this is going to give me r squared is equal to 3y. Which is, again, not quite done because I'm supposed to be having all x's and y's without any r's or thetas. So this is where we can now take my value for r squared and rewrite it as x squared plus y squared. And so we have that x squared plus y squared is equal to 3y, and this is now technically already my rectangular form. Now I can see because x squared and y squared are being added and they have the same coefficient, this is going to be a circle. But notice that we are going to be able to simplify this a little bit if we choose to complete the square. So notice that I could actually move things around and I could say y squared minus 3y. And so if I take that and I just keep those in parentheses, that's going to be equal to 0. So this is just another form to rewrite this circle so that we can see what the center and the radius are. And this is where we now add half of -3 squared. But if we add half of -3 squared, we have to subtract that same quantity, or rather 9/4. And now the purpose of this is so that we could now factor that trinomial. So here we get x squared plus, and now we have y minus 3/2 quantity squared. And if I add 9/4 to the other side, that's going to give me 9/4. So this is more accurate in terms of how to graph, because it's now in the form where I can see the center and the radius. So in one form, we went from rectangular and converted into polar. Now we're starting with polar and converting into rectangular. Now it's going to turn out that for a lot of these, I would much rather graph the rectangular equation for the linear one on the left, as opposed to trying to graph this one down here. But notice that even though this equation for the circle right down here is relatively straightforward, it's going to also turn out that it will be more simple for us to graph using the original form in certain circumstances. So let's start taking a look at how we can graph these equations in polar form, since we already know how to graph all of our functions in rectangular form. So in order to graph these functions, the most important thing to do is to start with some polar graph paper. Now these are very difficult to come by, but you can print these up from online, or I've also created one that's available as a link on our page, so that you can actually just print this up and graph using these concentric circles and their corresponding tables. But what we're going to do is start with this and say r equals 3 sine theta. Now, the most simple thetas to always pick are our quadrantal angles. So let's pick the angle 0, the angle pi over 2, the angle pi, and the angle 3 pi over 2. Now we don't have to choose 2 pi because it'll be plotted at the same place as 0. So when you plug in 0 and pi over 2 and pi and 3 pi over 2, we're just simply plugging it into here and recognizing what our quadrant or what our unit circle ratios are going to be. Then we're going to multiply it by 3. Now I'm going to also demonstrate first that we have to state what our radius is. So perhaps we want our radius to be 1. If we want each radius to be 1, then we want this first concentric circle to be 1 unit, 2 units, 3 units, 4, 5 units, 6 units, and 7 units. Or if we choose this to be 0.5 to spread it out a little more, then that would mean every 2 circles would be 1 unit, 2 units, 3 units, and so on. So that's what we're going to do. We're going to cause this to be r equals 0.5. R is equal to 0.5. So that means that my first concentric circle is 1 unit. My second concentric circle is 1 unit. My fourth concentric circle is 2 units. My sixth concentric circle is 3 units, and so on. All right. So if we plug these in, sine of 0 is 0 times 3 still gives me 0. So all that tells me is at the angle of 0, plot the radius of 0, which means plot the pole. We don't always plot the pole, and in fact, the pole is not oftentimes going to be part of our graph, but it happens to be here. So now let's go to pi over 2. Sine of pi over 2 is 1, so multiply that by 3, and we get 3. So we've just got to recognize that this represents the point 3, comma, pi over 2, which means point in the direction of pi over 2, and walk out 3 units. Now notice that's the third concentric circle, and therefore walk out this far. Now if we go to pi, at the angle of pi, sine of pi is 0, so we're now back to 0. So let's think about what that means. It means that I started at the pole, and as I rotated around, my point at pi over 2 became 3, but then by the time I got back down to pi, my answer came back to 0 again. So we don't know what this graph looks like other than these 2 points, but that's what we're seeing so far. And finally, 3 pi over 2. Sine of 3 pi over 2 is -1 multiplied by 3, and we get -3. So again, notice that that's the point -3, 3 pi over 2. Now keep in mind what the negative radius means. It means point in the direction of 3 pi over 2 and walk backwards -3 units, which takes me right back to the same exact point again at pi over 2. So it turns out that it looks like none of these other points, these points right over here, were duplicates. So we really didn't need to plot them a second time. All right, so why don't we go ahead and pick some values for sine of theta, or for theta rather, that are going to give some nice values for sine theta, which is why I like to pick the pi over 6 angles. So let's pick the pi over 6 angles because I know that sine of pi over 6 is 1/2. So 1/2 times 3 gives me 3/2, or 1.5. So we're going to go out 1/2, 1, and 1.5 at the angle of pi over 6. So somewhere along the angle of pi over 6, we're going out 1.5 concentric circles, which takes me to this point here. So now let's pick 5 pi over 6. 5 pi over 6. If we pick 5 pi over 6, that's in our second quadrant. So now sine of 5 pi over 6 is also 1/2 times the additional 3 gives me 3/2. So now we're going to the angle of 5 pi over 6, and we're walking out 3 concentric circles again, which puts me to here. So that's another point to my graph. And now we could also pick 7 pi over 6 and 11 pi over 6. But notice that sine of 7 pi over 6 and sine of 11 pi over 6 are both -1/2. So those values become -3/2 and -3/2. I'll just write out one of these points. Notice that this -3/2 and 7 pi over 6 is just telling me to point in the direction of 7 pi over 6, which is in this direction, and walk backwards, which would put me to the same point that's already there. Which is why notice that I don't really need to use both of those points because these points are also duplicates of the first pink points. So let's look at what we know. We know that when we started at the angle of 0, we started at the pole. And as we started to move from pi over 6 to pi over 2 to 5 pi over 6 to pi, that we started to get this point connecting to this point, connecting to this point, connecting to this point, and connecting to this point, and then starting over again. But that's only using 4 points. I like to come up with at least 8 points when we're coming up with our values. So I'm going to go ahead and realize that when I pick points that are in the 3rd or 4th quadrant down here, those are going to give negative answers that spit me back into the 1st or 2nd quadrant. So I'm only going to pick 1st and 2nd quadrant answers from now on. So let's pick pi over 3 or pi over 4 and pi over 3. All right, well, sine of pi over 4 is √2 over 2 times 3 gives me 3 √2 over 2. Now, if you punch that into the calculator, you would see that 3 times √2 is about 4.2. Divided by 2 gives me approximately 2.1. So it's not going to be exact, but we know that at the angle of pi over 4, we're going to move out 2.1 concentric circles, which would be a little past 2. and that would be a point as well. Now, if you plug in pi over 3, pi over 3 gives me a value of root 3 over 2, times 2 gives me 3 root 3 over 2. But again, if I want to plot that radius, I have to know that that ratio, root 3, is going to be 1.73 times 3 gives me about 5.2. Divide by that by 2, and we get approximately 2.6. So now at the angle of pi over 3, somewhere along this line, I'm going to go out 2.6 units, which is, well, here's 2. Here's 2.5. So 2.6 is a little past here. And therefore, there's another point. This is why it would be a good idea to perhaps pick my pi over 3 angles as well in the second quadrant, 2 pi over 3, and my pi over 4 angle in the second quadrant as well, which would be 3 pi over 4. If we plot those, then notice that I would get the same exact y values because sine is positive in both the first and second quadrant. So here I would get another 2.6, and here I would get another 2.1. So that means that the angle of 3 pi over 4, I'm going to be at 2.1. At the angle of 2 pi over 3, I'll be at the angle of 2.6. So hopefully we can start to see what this shape might be turning into here, because I need to start at the pole and start connecting the dots as I move to increasing angles, to pi over 6, to pi over 4, to pi over 3, to pi over 2, to 2 pi over 3, to 3 pi over 4, to 5 pi over 6, and back again to the angle of pi. So notice that as I start moving away around my curve, it turns out that r equals 3 sine theta is a circle. But we should know that it was a circle because we actually already came up with the form of that circle right over here. If we take a look at this circle has a center of 0, 3/2, which means that I would plot my center at 0, 1.5. The radius is going to be the square root of 9/4, which means that the radius is 3/2. So that's why I would go 3/2 up, 3/2 down, 3/2 to the side, and 3/2 to the side. And sure enough, notice that it is in fact a circle. We didn't have to convert it into rectangular form to see that it's a circle because plotting some angles with their corresponding ratios gave me that same result. I'd like to graph one more polar equation just to see what happens now. Now, the prior example, we were able to convert into rectangular form and come up with another equation that we were able to graph in rectangular form. But now we've made a couple of minor little adjustments to that last example. First of all, we rewrote this in terms of cosine instead of sine. And instead of the angle being theta, we see that the angle is 2 theta. And so we have to do something very similar to what we did in the previous one by coming up with a table of values. Now we're typically going to, again, start off by choosing our quadrantal angles, but in a very similar way to we noticed in the last problem, sometimes coming up with these gives duplicates of points. So it's maybe pointless for us to actually come up with all of these values. But notice that if I were to plug in 0, we're finding out what cosine of 0 is. So we're plugging in 0. But notice what's important here is that we are first doubling the angle before calculating cosine. So when I double the angle, what this really gives me is 3 cosine of 0. And 3 cosine of 0 gives me 3. So we first of all have to do the same thing that we did in the last one and label what we want our concentric circles to be. So why don't we do the same thing and label my r value again at 0.5. Okay, well, 0.5 says that in the first concentric circle is 0.5, so this is 1, this is 2, and this is 3. All right, so this is telling me that at the angle of 0, plot the radius of 3. And there's our first point right here. Now let's plug in pi over 2. Now keep in mind, I'm taking pi over 2 and first multiplying it by 2, which gives me pi. Now I'm finding cosine of pi and multiplying that by 3. Cosine of pi is -1. So multiply that by 3 and we get -3. So what does that mean? That means that if we were to take a look, if we were to walk, start by pointing in the direction of pi over 2, we're going to walk backwards 3 units, which means we're actually going to be down here. So therefore, this is the point -3 pi over 2. So let's take a look at pi then. So if I start with pi, I'm now going to be plugging in pi and doubling it. So I get 2 pi. Take cosine of that, then multiply by 3. Well, cosine of 2 pi is 1. So now I'm going to go out 3 units in the direction of pi, which means in the direction of pi, walk out 3 units. So far this is starting to maybe look like a circle. I don't know, maybe this is a different type of circle. So now if we try 3 pi over 2, again, double that to become 3 pi. Cosine of 3 pi is -1. So this becomes -3. So let's practice that negative radius. Point in the direction of 3 pi over 2 and walk backwards 3 units. So notice that my next point is right here. And by the time I move around to 2 pi again, I'm at an angle of 3, which means that from 0 to pi over 2, I'm actually getting that point next, then that point, then that point, then that point to get me back to the beginning. Now, I don't know what else it's going to look like, but that's why I should pick a few new points. So now maybe we choose to pick some values that are going to give me some simple answers. So maybe we pick some pi over 6s, okay? So let's pick pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now notice what these did. When I multiply pi over 6 times 2, that's going to give me pi over 3. So what I'm really doing is calculating cosine of pi over 3, then multiplying it by 3. Well, cosine of pi over 3 is going to be the x-coordinate of pi over 3, which is 1/2, and therefore we get 3/2. So at the angle of pi over 6, we're saying pi over 6 along this angle, go out 1.5, which puts me on the 1.5 radius circle. So I now know that it's going to start at 0, and it's going to go to pi over 6, which is right here. And somehow it will then connect to pi over 2 when we get down to here. Okay, so now let's pick 5 pi over 6. The only difference there is that now we're going to get 5 pi over 3. 5 pi over 3 is in the 4th quadrant. And so cosine of 5 pi over 3 is also 1/2 times 3 gives me 3/2. Okay, so at the angle of 5 pi over 6, 5 pi over 6 is going to be over here. So 5 pi over 6 takes me out 3/2. So at that angle, I get, oh, it's the wrong circle. I get to here, 1.5. It should be on the same circle as this one right here. There we go. Okay, so now just to see how this connects, I have to connect the value at 0 to the value at pi over 6, to the value at pi over 2, to the value at 5 pi over 6, to the value at pi, to the value at 3 pi over 2, back to the value at 0. So it's still really unclear what that looks like. So we're just going to keep picking a few more values and see what happens. Okay, so let's pick 7 pi over 6. 7 pi over 6 is going to be doubled to get 7 pi over 3. Then we take cosine of 7 pi over 3, which is in the first quadrant, so 1/2, times 3 gives me 3/2 again. So we're saying at the angle of 7 pi over 6, you're going to go out 1.5 again. And you can see that that same thing's going to happen at 11 pi over 6, so we'll skip the work there. At 11 pi over 6, I will get to that point. Okay, so we should get 3/2 there. All right, so let's just label real quick what's going on. This is the angle at 0. This is the angle at pi over 6. Now notice, even though the angle up here is pi over 2, notice that when we plugged in pi over 2, we actually got -3, right? So at the angle of pi over 2, we actually shot down to this point here, which is the actual value at pi over 2. This is the value at 3 pi over 2. This is the value at pi. Here we have the value at 5 pi over 6. Here's the value at 7 pi over 6. And finally, the value at 11 pi over 6. So we might be able to tell a little bit more of what's going on. I have to go from 0 to pi over 6 to pi over 2. Then from pi over 2, I got to hit pi over 6 to pi. But then I got to hit 7 pi over 6, up to 3 pi over 2, down to 11 pi over 6, and then back to 2 pi. Okay, so it's getting to be some sort of really peculiar looking curve. So I'd like to go ahead and maybe pick a few more points. So let's pick something like pi over 4. And look at why I'm picking pi over 4. If I double pi over 4, I get pi over 2. Take cosine of pi over 2 to get 0. And when you multiply 3 times 0, you get 0. So notice that that told me that the pole was actually part of my graph. Now notice that same thing is obviously going to occur if I pick 3 pi over 4 or 5 pi over 4 or 7 pi over 4 as well. It's going to continue to go through the pole every time it hits pi over 4. So now we've got to start thinking about, as we move through, I've plugged in the values of 0, pi over 6, pi over 4, pi over 2, and so on. And when I've gotten these values, I'm going to start connecting the dots as I go around. I have to connect the dot from 0 to the angle of pi over 6, to the angle of pi over 4, to the angle of pi over 2, to the angle at 3 pi over 4, which will hit the pole again, so it's got to go back through the pole. Now to the angle of 5 pi over 6, now to the angle of pi, to the angle of 7 pi over 6, back to the angle of 5 pi over 4, which is at the pole again. And now from 5 pi over 4, the next angle I plugged in was 3 pi over 2, so I got to come way up to 3 pi over 2. Now I've got to come back to the pole at 7 pi over 4. Now I've got to connect the dot at 11 pi over 6 and go all the way back to 0, which is now the full rotation of 2 pi. And what we should recognize now is that this formed what we refer to as a 4-leafed rose. There would have been no way for us to graph this in rectangular form. Because notice it's not a function. It's got multiple non-functions, multiple petals. It doesn't pass the vertical line test. The only way that we would be able to actually plot this is for this equation to be in polar form. So we finally have an actual purpose of why polar form is necessary and helpful. It gives us all of these different types of graphs that we wouldn't have been able to graph by using simply rectangular form. So the way that we're typically graphing, remember, is that even though we plot certain values, like the quadrantal angles, and then we plotted some pi over 6 angles, and we plotted some pi over 4s, when it comes time to graphing, we always need to go in order of angle. So we plotted 0 first, then we plotted the value at pi over 6, then the value at pi over 4, then the value at pi over 2, and then the value at 5 pi over, or 3 pi over 4, and we continue in that fashion. And that's how we can graph any curve in polar form. Now, just as we've been able to know what the shape of a particular rectangular graph would be just by seeing the shape of the equation, we should also be able to eventually be able to tell what a polar graph will look like just based on its equation. And there's a few that are pretty common here. First one we went over was r equals 3 sine theta. And we recognize that 3 sine theta was a circle symmetric to the y-axis. But if it happened to be negative 3 sine theta, the only thing that would change is that it would be the circle down below, still symmetric to the y-axis. But now if we had a cosine theta, we should still see that that would be a circle, except now it would be reflective to the x-axis, while if it had a negative a value, it would be a circle on the other side. Now, the next ones here are referred to, there's a few that are called limniscutes that look like infinity symbols, and that typically happens whenever you have r being squared, while the angle is 2 theta. I want to focus a little bit on these limasomes. The limasomes are anytime you have a sine theta term or a cosine theta term with a constant added or subtracted from it. So for instance, maybe we had 1 plus 3 cosine theta. Now, anytime an equation is purely in terms of cosine, it's always going to be symmetric to the x-axis. Now that should be pretty obvious why, because if I pick an angle in the first quadrant and look at cosine, it's going to have the same value in the fourth quadrant. So it'll be symmetric to the x-axis. But if I look at a graph symmetric to the y-axis, the reason for that is if I look at this angle and look at the sine value, the value of sine is going to be the same in the second quadrant, which is why anything involving sine theta will be symmetric to the y-axis. So these different limasomes start to happen. This is called well, this is first of all called a cardioid. So if you ever see that the a and b values are the same, perhaps you see 3 plus 3 cosine theta, then you're going to come to a little point right here, kind of like a heart, and it's going to rotate around. This one right here is referred to as a limasome with an inner loop. So what happens here is that it'll start to come around this way. As it comes around, it'll inner loop and come back around, and therefore it'll loop on the inside of itself. That's going to happen when a divided by b is bigger than 1. So in a situation where we might have 5 plus 3 cosine theta. Okay. This one over here is referred to as a dimpled limasome, just because it's like a dimple on somebody's face. Okay, it just dimples a little bit. It never comes to a full point, but it just dimples before it comes back around. That's if a divided by b is somewhere between 1 and 2. Now, it's not always necessary to memorize these, but just recognize that there's going to be different shapes depending on the shape of the equation. Down here, we ended up graphing this one right here. Okay, only we graphed the one that said r equals 3 cosine of 2 theta. Notice that if the n value here is 2, then we have 4 loops. If the n value is 4, then we have 8 loops. And so it looks like we've doubled the amount of loops for the coefficient of what that angle is. But if the n value happens to be odd, now notice that an n value of 3 gives 3 loops, and an n value of 5 gives 5 loops. And so we'd be able to tell basically the fact that anytime you have a multiple of an angle, you know that you're going to get some sort of rose curve that's going to have multiple petals. So all of the polar curves, you can notice, are things that we wouldn't be able to graph in rectangular form, because not only are they not functions, but it would be a very difficult equation to have to plug in x's to get corresponding y's. So instead, if we think of it in terms of rotation, we can plug in thetas and get corresponding radii.